Good evening and good morning. And today our session will focus on the wind retrieval algorithm, which is the core of our scientific applications. So today's session will be hosted by Professor Chen from National Central University.
Okay, hello everyone. This is Qianhua speaking. And so we have three speakers today in this session. The first one is myself, and the second one is Dr. Balasubramania from University of Michigan. The third one is Professor Tsai, also from National Central University. Each of us, we will have a talk around 40 minutes. So we have already recorded our presentation. We should proceed the next talk. Okay, so the next talk will be presented by Professor Tsai from National Central University. Yeah, please.
Thank you, Chairperson. This is Lung-Chih Tsai from GPS Art and Center for Space and Remote Sensing Research of National Central University, Taiwan. I'm happy to present our recent study on the software-based GPS-R receiving network in Taiwan for ocean monitoring. Actually, this study is supported by a MOST DFG joint research project named DEARIST. It is development and application of a GNSS remote sensing technique for Earth observations. The co-workers include myself, Lung-Chih Tsai, and Professor Xinyi Su, Professor Hua Qian, Professor Zhao Han Liu on the Taiwan side, and Professor Hana Su, Professor Jens Wicker, and Professor Marty Elzedev on the Germany side. For the talk, the content includes first, introduction of GPS signal and code structure. Second, development and architecture of a software-based GPS receiver. Third, GPS reflectometry observation on sea surface wave. Fourth, result and its validation. And finally, future works. At first, this page lists some basic application of GPS system. It includes navigation, surveying, geodynamics, geophysics, and remote sensing on troposphere, ionosphere, and ocean, and time and frequency transfer, and the others. For this talk, it will focus on the remote sensing application on ocean observation. For a software-based GPS receiver, it is important for understanding GPS signal structure. As shown, this well-known GPS signal include L1 band signal and L2 band signal. L1 band signal include CA code at 1.023 MHz, and the other peak code at 10.23 MHz. And L2 band signal include the P code signal only. Those codes are modulated with using addition and modulator to be final GPS signal. The right-hand panel just shows the L1 band signal spectrum here. So in this study, we just process the L1 band the CA code only. This page shows GPS navigation message structure on CA code. It includes one CA code in every 1 millisecond, and then one navigation data in every 20 milliseconds, and then one word in every 600 milliseconds, and then one subframe in every 6 seconds, and one page in every 30 seconds. So totally, that includes 25 pages in every 12.5 minutes. So we note the basic GPS signal structure that is a CA code in every 1 millisecond. It includes 1023 chips for each CA code. This page shows the development and structure of our software-based GPS receiver. It's noted that our GPS software receiver can be used on direct GPS signal receiving for IR field observation, we already developed 3 stations for IR field scintillation observation at Zhongli, Hualien, and Pingdong. And the software GPS receiver also can be used on GPSR observation on ocean web. We already built 2 stations at Xinwu and then Lan Yu Island. This page shows a flow graph of software-defined GPS receiver. We know that a software GPS receiver also needs somewhere. It includes a receiving antenna and RF front-end module to produce baseband signal. You also call the I and Q component signal after digitized. After that, the baseband signal can be processed by software in a computer. We also know different channels can be used to process the signal from different satellites. For such as data processing include the signal acquisition, data tracking, and data decoding for navigation message. At the next, I'd like to introduce the structure of our software receiver. Actually, it's just the implement the part of a GPS signal acquisition. The first step is generation of a CA code. First, we use the GPS two-line element to design visible GPS satellite. And as you know, the GPS satellite have a unique CA code. And CA code actually is one type of the Go code. The CA code, they have 2 gates. Each gate actually is a 10-shift register, and to produce a sequential of what we say the pseudo-random noise code. At the next, based on GPS two-line element information, the label class CA code signal of visible GPS satellite and the corresponding Fourier transform can be obtained based on the FFT transformation. On the other side, the baseband signal and its Fourier transform can be derived. The fourth step of GPS signal acquisition is a point circuit correlation technique. It computes the complex conjugate modification of 2 spectra from the replica signal and also the baseband signal. And then we compute the inverse Fourier transform of such a signal product to obtain what we say the time delay profile from visible satellite. This example shows the result of direct observation. Usually, we can obtain 6 to 10 channels, I mean the time delay profile, from one set of GPS satellite signal. If we accumulate a long-term observation, we can produce such an IPP map. This page, I list some characteristics of a software-based GPS receiver. The advantage include low price, high sampling rate, being a flexible system for online, offline single processing, and more application on customized service, for example, IR field scintillation observation and GPSR observation. I'd like to note the sampling rate can approach the maximum value of 1 kHz. On the other side, the disadvantage include huge data because of high sampling rate, not real-time management, processing one band signal only in one system. As I mentioned, one application of our software-based GPS receiver is working on IR field scintillation observation. We have built 3 stations at Zhongli, Hualien, and Lung-Chih to direct receiving GPS satellite signal and working on the IR field scintillation observation. Usually, we can obtain 20 to 30 IPP position for such IR field observation. If we accumulate the whole day, I mean the long-term observation, we can produce such the IPP map and even the scintillation map. For direct GPS single observation, this page just shows an example of ionosphere scintillation and Doppler offset observation from a software-based GPS receiver. From the left-hand figures, the satellite signal can be received by a right-hand circular polarization antenna. In this study, we use a Novatel GPS 702 module antenna to receive the corresponding signal. And then we use USRP B200 mini module to produce baseband signal. Such baseband signal can then processed by the software in the notebook computer. The right-hand figure just shows a 24-hour result. It includes elevation angle profile. The color is showing the different GPS satellite. And it also includes data acquisition correlation result and even the S4 index value profile and vertical S4 value profile and then Doppler frequency profile in different satellites presented by different colors. For scintillation, ionosphere scintillation observation, usually we can obtain what we say the ionosphere scintillation index map or S4 index map as shown as this figure. So different time we can see what's the variation. In the following section, I will focus on introducing GPS brevettometry observation, its single processing, and corresponding study on sea surface observation. This picture is copied from the paper by Zaffaroni in 2000. The picture shows the geometry of GPSR observation. As shown, the GPS signal is transmitted from a GPS satellite at the right-hand circular polarization to be reflected by sea surface and is received by a left-hand circular polarization antenna of a receiver. We like to note there are two sets of lines on the GPSR observation area. One group is constant delay line, and the other group is a constant Doppler lines. Both sets of lines just show the area for GPS signal reflection and scatter, and to produce a usual GPSR observation product we name delay Doppler map. One of the usual GPSR observation product is delay Doppler map, or we call it DDM. This picture shows some typical GPSR DDM result from Cygnus satellite produced by Kreuzer in 2015. Both pictures show typical horseshoe arc shape. When wave speed is low, such a DDM horseshoe arc shape is asymmetric. However, when wave speed is high, such a wave speed, the DDM is unsymmetric as shown as this. As introduced, we have set up two GPSR stations in Taiwan. One is located at Xinwu at North Taiwan. The station has a 35-meter altitude, and the other GPS observation is located at the Lan Yu Island. The station's altitude is about 342 meter altitude. I also like to recommend Lan Yu Island. It's a very good place for snorkeling. I did enjoy snorkeling there once. This picture introduces the GPSR observation on sea surface web at Lan Yu. Lan Yu is a small island with size about 40 km square. We note there is a CW observatory located at the center of the island. Our GPSR station was set up in the CW observatory and have a 2 GPSR systems facing 2 different directions. One antenna is facing to the northeast direction, and the other system antenna is faced to the southwest direction. The center picture just shows the GPSR spectral point position and corresponding track in color presenting different GPS satellites. At last, we know that 2 GPSR verification position was set up in this experiment. One is based on the buoy measurement, the other is based on the WRF modeling data. As mentioned, the usual GPSR observation product is what we say the delayed duplet map, or DDM. We did try to produce DDM from our GPSR observation. This experiment just shows our DDM result. For in our observation, we can see we received 2 GPSR signals from 2 different GPS satellites. The left 2 panels just show our simulated DDM result. So you can see they have a very strong at a reflection point. However, 2 tail signals are very weak. Also happened for the other GPS satellite. The center, the reflection signal is very strong. However, the 2 scattered tail signal is very weak. That's happened for our physical observation as shown as the 2 center panel picture. We can see very clear center, the center signal there. However, we cannot see typical the tail from the what we say the DDM, the structure. As described, DDM is not a good method for GPSR observation analysis in this study. It is because our GPSR station is static. Therefore, the relative velocity to satellite or even the relative Doppler frequency is not large for typical DDM observation. In this study, we will introduce a random wave spectrum analysis method to derive sea surface wave frequency. As mentioned, the upper left panel figure shows GPSR spectral point position and track in different color to present observation from different GPS satellites. Usually, we can track 1 or 2 GPS signals at each of Lan Yu's system in any time. As shown as the upper right panel figure, we record 70-second peak of GPSR signal acquisition result, as shown as the yellow and even the light blue color profile from the satellite number 22 and number 11 satellite signal. The gray color profile just means the single locked status. Using both of the Fourier and even the MAXIM Entropy Method, the corresponding spectrum are shown as the 2 bottom figure. We know that the spectrum between the 0.1 Hz and 2 Hz are caused by sea surface. Such a result happen for both methods, applying the FFT method and even the MAXIM Entropy Method. Such a spectrum are not shown, are not seen from the direct observation. This page shows sea surface wave determination by Fourier spectrum analysis. This figure shows a whole day Fourier transform analysis result on the day 346 in 2019. So if we focus on the GPSR observation around the 9 UT, the corresponding Fourier transform spectrum is shown as this figure. The different color just mean different GPSR zenith angle. We know that we do not try to derive the peak spectrum frequency to be the sea surface wave frequency. However, what we use is a random wave spectrum moment to derive the mean frequency and to present the sea surface wave frequency. This page shows the sea surface wave frequency determination using another method, the MAXIM Entropy Method on spectrum analysis. Based on the same data as shown as the last page, if we focus on the GPS observation around the 9 p.m., the corresponding MAXIM Entropy Method spectrum is shown as this page. The same, different color mean different GPSR observation zenith angle. You can see the MAXIM Entropy Method, the spectrum analysis, the spectrum resolution is much better compared to Fourier transform. As shown as the last page, we did not try to get the peak and even bottom to characterize the GPS observation. That's because such method cannot derive the reliable result. However, what we do, we just using the random wave moment to derive the mean frequency to present the sea surface wave frequency. I'd like to know, using the MAXIM Entropy Method, the result is much reliable compared to Fourier transform method. So the following study, I just present the MAXIM Entropy result. At next, the observed or obtained mean frequency using random wave spectrum analysis is not the final sea surface wave frequency. To obtain the final sea surface wave frequency, we need to include the effect of specular point positioning, or what we say the SPP movement. The corresponding frequency equation between the observed wave frequency and the velocity of the SPP is shown as those as this equation. Continue the last experiment we showed. We have shown the SPP velocity as shown as the gray color as here, and the cutted dot just mean the fitted observed wave spectrum result, and the final wave frequency is shown as the red color dot. After the wave frequency is obtained, of course we also can obtain the sea surface wave period. These two figures just show the sea surface wave period map obtained on December 12 and December 18 in 2019 using the MAXIM Entropy spectrum analysis. However, we show the different color to present a different period. However, usually we like to present the confidence area based on what we say the first Fresnel analysis. So this equation just shows what's the FFT ellipse, what's the distance of the SPP positioning from the receiver, and also the FFZ ellipse major axis length and even the minor semi-axis length. The same. Based on the hydrodynamic law, we can obtain wave velocity from the wave frequency result. These two figures just show the sea surface wave velocity map obtained on December 12 and December 18 in 2019 using NEM spectrum analysis. We show the GPSR observation area based on what we say the FFZ. The corresponding equation and the definition is shown as this figure 2. As shown, the wave frequency map based on first Fresnel law are not clear. So we apply rate-breaking smoothing method to get better reliable, the readable mapping result. This figure just shows the final wave period mapping result on every 2 or 3 days during December 12 to 26 in 2019. Similar, the sixth figure just shows the sea surface wave velocity map after rate-breaking smoothing on every 2 or 3 days during December 12 to 26 in 2019. In this study, we will use the CW buoy measurement to verify our GPSR observation. This picture just shows some CW buoy measurement result. It includes the wind wave, wind velocity, wave height, or even the current velocity profile in 5 days. And I also showed some of the azimuth angle information there. This one is the result of buoy wind velocity, wave height, and current velocity profile during the day from the 5:51 to 5:55 in 2019, and I also showed the zenith angle for the reference. In this study, we used 2 different data, including buoy measurement and WRF modeling data to validate GPSR sea surface wave frequency measurement. As shown as this figure, we note the blue dot is the buoy position. The buoy validation position is located in the area of northeast direction, and the red square is the WRF validation position and is located in the GPSR observation area of southwest direction. We collect all GPSR observation in the distance less than 2 km to the validation point position and compare the validation data. The total experiment duration has 21 days. The left scatter plot is showing the GPSR validation result with buoy measurement. We note the x-axis is showing the GPSR final wave frequency, and the right y-axis is under buoy wave measurement in Hertz, and the right y-axis is under buoy wave height in meter and buoy wind velocity in every 5 meter per second. We note the blue dot just showing the scatter plot of GPSR wave frequency versus the wave frequency from the buoy measurement. The correlation coefficient, the correlation value is quite low, just about the 0.036. However, the mean wave frequency from both of the GPSR and even the buoy, the wave frequency, has about the same value, about the 0.2 Hertz. The low correlation value may be caused by the low pass effect on the buoy frequency measurement. The red dot just showing the scatter plot of GPSR wave frequency versus the buoy wave height. You can see the correlation coefficient value is quite high, can reach about 0.64. And the third correlation, the analysis is shown in the black dot between the GPSR wave frequency and the buoy the wind velocity. The correlation coefficient also is pretty high, can reach about 0.66. The right scatter plot is showing the GPSR validation result with WRF modeling data. The x-axis is under the GPSR final wave frequency, and the left y-axis is showing WRF wave frequency, and the right y-axis is under WRF wave height. Similar to the correlation analysis with the buoy measurement, the correlation, the blue dot just shows the scatter plot between the GPSR, the final wave frequency, versus the WRF wave frequency. The corresponding correlation value is quite low, just about the 0.4. However, the scatter plot between the GPSR wave frequency versus the WRF wave height is shown as the red dot, and the corresponding correlation coefficient is much higher, can reach about 0.47. I'd like to conclude that because the WRF modeling data is also based on the CWB's buoy measurement, so have a similar effect to the validation with the buoy measurement. However, such a correlation analysis is not so good, maybe just because they have some global mapping reason. And I also like to conclude the validation of the GPSR observation actually is not bad, because we still can get a pretty high correlation relationship between the GPSR final wave frequency versus the wave height and even the wind velocity. As described, we have installed, set up a second GPSR station at the Xinwu. However, the antenna height is much lower compared to the Lan Yu's station. It's just about 35 meters. So multiplied by a factor about 60, the longest distance can reach is just about 2 kilometers. As described, we have implemented the DDM processing on such a GPSR observation. We expect can receive the signal not just at the reflection point, also corresponding the constant delay point scattering signal, and produce just like this the 3-dimensional DDM map. Similar to the Lan Yu GPSR experiment, we have simulated physical scattering area on the Xinwu observation. These two figures just show the physical scattering area simulation, and we expect to have a typical DDM structure as those simulation results. However, from the two right figure for the real measurement, as seen, we can see very strong reflection signal at the spectral positioning point. However, we cannot see a typical horseshoe-shaped DDM structure. The same as the Lan Yu observation, we believe is because there is a very low relative Doppler velocity, and it induced cannot obtain a typical DDM shape and used to drive the wave frequency result. So at last, just like the Lan Yu experiment, we try the random wave spectral analysis to derive the wave frequency result. So we execute a random wave spectral analysis on such a time series record of peak signal amplitude from the GPS satellite signal, and get the mean frequency using the spectrum moment analysis. So from this spectrum, you also can see some typical spectrum from the GPSR observation at a frequency about 0.1 to a couple hertz of frequency. So these two figures just show the sea surface wave development by maximum entropy estimation at the Xinwu on day of year 269 and day of year 300 in 2019. So different color just mean the signal from different GPS satellite, and the blue line, the black line just show you the buoy measurement result. The bottom two figures showing the same result, but in color with different zenith angle. I like have final remarks as shown as follows. First, software-based GPS receiving system can derive the sea surface wave frequency and period using the GPSR reflectometry technique and random wave spectral analysis on GPS single amplitude measurement. Second, It is also possible to derive the ocean wave speed based on hydrodynamic laws. However, this is not direct measurement, and there is no wave direction information. Third, the GPSR sea surface wave observation have high correlations with buoy wave height and wind velocity measurement. And then, it's difficult to derive the mean square slope per meter of sea surface wave using delayed Doppler map from ground-based GPS receiving system because of low Doppler velocity between GPS satellite and ground-based receiver. At last, I'd like to thank CW Taiwan for their support on this GPSR experiment. I'd like to use this page to present all the future work of our study. We expect to build more GPSR observation stations in east of Taiwan to routinely monitor the sea state of the East Ocean of Taiwan. Thank you. This is all my talk. I'd like to thank you for your participation and hope you can enjoy it.
Okay, thank you, Professor Tsai. So now it's time for open for questions and comments. Is there anyone who would like to ask questions? Okay, so if there is no further questions, I will close this session. And so thank you everyone for joining this meeting today.